Okay, folks, here we go. So this video is going to kind of run through our current review for our circular motion quiz, which we have upcoming, and it's mostly free response problems. I would suggest that you go back and look at any conceptual situations we've looked at throughout the unit as well. Likely you'll see some conceptual questions on the quiz as well as free response questions. So let's just kind of run through the free response questions here. So we're starting off, we see we have a 50 gram, which is a 0.05 kilograms. We need to be in kilograms, meters, and seconds when we calculate it with our equations. So our air hockey puck is rotated on an air hockey table in a horizontal circle with a string. So that means the circle is horizontal and the tension causing us to move in a circle is also going to be horizontal. So we just have this scenario right here, a horizontal circle with a horizontal tension. The length of our string is 50 centimeters, 0.5 meters. So that's meant to be the radius of our circle. And the tension of the string is 10 newtons. What's the frequency of the air hockey puck in revolutions per minute? So our strategy here is going to be using the tension that's known to find a speed, and then we can find our frequency from the speed. So we're going to start with Newton's second law. We're going to take our centripetal force, rewrite it as tension, because tension is allowing us to move in a circle now. A is V squared over R, and you'll see basically a combination of these two equations kind of set up right here. We have the net centripetal force and then mv squared over R. But you could also start with this and make your A substitution. Okay, tension is given as 10, mass and radius are both given, so we can solve for a speed V, and now we have to go from meters per second to revolutions per minute. So seconds to minutes is easy enough. I don't have to go over that, but meters to revolutions tends to trip people up sometimes. So we're starting off with 10 meters over 1 second. To go from meters to revolutions, we're going to use the circumference formula, because one trip around the outside of a circle, you've gone a distance equal to the circumference of that circle. So one revolution is equal to a certain number of meters for the circumference. So 2 pi times r, where r again is given. So do all that math. You want to probably put some brackets if you're trying to put all this in one go in your calculator, which you don't have to do, but you should get hopefully 191 revolutions per minute as a frequency. Frequency is always going to be some number of circles or revolutions divided by some number of time. The period, which we see up here, period, capital T, that's the time for one revolution by definition. So the period is some number of seconds divided by some number of revolutions. Anyway, next, the situation will be the gravitron. So we're moving in a horizontal circle with a horizontal normal force, acting as our centripetal force. So for the gravitron, we are standing with our back against a wall. We may have had the floor underneath us, but the ride is supposed to spin around fast enough so that we are feeling pinned to the wall and the floor drops out from underneath our feet and we're stuck to the wall. So we have gravity pulling us down, but if we're not actually going down, something's got to be doing the work to hold us up. So that force holding us up, not letting us slide along the wall downwards, is static friction. So we get UFN going up. And then we have our normal force going into the center of our circle because we're standing with our back against a vertical wall instead of standing on a horizontal surface. Okay, so this is pointing into the middle of our circle. This is our centripetal force. So we can start with Newton's second law for all of our up and down forces. We're not going up and down, so those two are equal to each other. So we can make our substitutions for those two forces that we've been doing for quite some time now. The fact that we're moving in a circle can't be ignored either. So we have Newton's second law for circular motion. The centripetal force is just the normal force, and a v squared over r, all that. So v we can plug in. We can either do 2 pi r here, and then square it. And when we do that, we get 2 squared, which is 4, pi squared, which is just pi squared, r squared becomes r squared, and t squared is t squared, basically. Right. So all that goes in for v. Or if we had the information, we have a period of 2.6 seconds. We don't have the radius. We're looking for the radius. So that's why we got to make this substitution. Anyway, okay. Normal force, mg over mu. Sorry about that. That can go over. We know everything. Mass is going to cancel. So g, coefficient of friction, the period is given. Those are just numbers. We can solve for the radius. There you go. Bing, bang, boom. Moving on. Car going around a turn. So this is car going around a turn on a flat road. So again, a horizontal circle with a horizontal friction acting on our car. as our centripetal force. So we're going 20 meters per second. We have a coefficient of static friction 0.72. We have the size of our turn 40 meters. We need to figure out will we or won't we safely navigate this turn. So one way you could do this by solving for, how fast can I go given the size of my turn and the road conditions? What is my actual speed that I can go as a maximum? And then compare that to how fast I'm actually going in 20 meters per second. So we have a normal force going up, weight going down. We have our friction going into the center of our circle because it's not allowing us to slide and drift away from the center of that circle. So Newton's second law for circular motion. The centripetal force is the force of friction. We can plug in mu Fn, and Fn going up is equal to mg going down, which we see with Newton's second law right there. We're used to that result. So Fn becomes mg. Masses can cancel, and we can solve for the speed v because we know the coefficient and the size of our circle in terms of the radius. So we would get 16.8 meters per second. That's the maximum safe speed we can go. We are actually going 20 meters per second, so we're going too fast. This is not a great situation to be in. The other way you could do it is by solving for the coefficient of friction that you would need given how fast you're going and the size of the circle. So if you have a coefficient of friction that's less than what you need, then that's not great. And if you have a coefficient of friction that's more than what you need, then you have more friction than you need. You're okay. And then lastly, you could solve for the size of the circle and go from there. So, okay, next up is our kind of next class of things. So we have some forces at angles here. We have basically a game of tetherball, even though it's not called tetherball, but we have an object moving in a horizontal circle, but the tension on that object is going at an angle, as opposed to before when it was just pointing into the center of our circle. So it's kind of a second class of upper class of problem here. Anyway, we have our weight going down. We have tension at an angle, but that's broken up into x and y components. All right. If we know the angle that the tension with the string is making with the vertical, then we know what this angle is there. So we would use sine for the x component and cosine for the y component. Now, we're not going up or down. We're moving in a horizontal circle. So tension y and weight have to be equal to each other, which is what we see here. And then we can, again, tension y is going to be our tension times the cosine of our angle that's given. Ftx in this case is what's doing the work to move us in a circle, not the force of tension. Ftx is what points directly into the center of our horizontal circle because it's a horizontal force. So Newton's second law for circular motion, replace with Ftx, replace with Ft sine, and then we can merge these two equations together through the tension. So sine over cosine becomes tangent, which is something you would get if you needed it. Masses cancel, we can plug everything in, and we would get how fast the speed is going of 1.085 meters per second. Next would be the car on a bank's turn. So we have our weight going down. We have our normal force perpendicular to the surface. We have that broken up into horizontal and vertical components. So Fny, Fnx. Now Fnx pointing horizontally into the center of our horizontal circle that we're traveling around as we go around this track is our centripetal force. We're not going up or down. So the normal force in the y direction is equal to our weight going the opposite way. And we see that result right here. They're equal to each other. Fn is going to be, Fny is going to be the normal force times the cosine of our banking angle. So the angle of the embankment down here is how much the normal force is being deflected away from formerly being purely up and down. So our angle here is the same as our angle tucked in there between Fn and the vertical. So again, cosine is going to get us y. So we make that substitution, move things around so they're equal to each other, and then switch to the fact that we're going in a circle. So Fnx is our centripetal force. It can be rewritten as Fn sine theta. Again, sine over cosine becomes tangent, which you would get if you need it. Masses are going to cancel when we move everything over. And then we can solve for what we're looking for. We're looking for the angle that we make for the embankment so that we don't need any friction to go around this turn whatsoever, given the speed and the size of the turn. So we would want 29 degrees. A next set of problems involves a vertical circle with the normal force also being vertical, either pointing into or away from the center of the vertical circle, and whether or not we are upside down at the top of the vertical circle or upright at the top of the vertical circle. We're always going to be upright at the bottom of our vertical circle. So here's the situation. For any of these circular motion scenarios, our centripetal acceleration always points into the center of our circle. So AC points in, AC points in, AC points in. All right, so when we're at the top, it points down. When we're at the bottom, it points up. Doesn't matter if we're upright or upside down at the top. We are always having a centripetal acceleration that points into the center of our circle. Our centripetal force, in terms of the net centripetal force, also points into the middle of our circle in most cases. Oh, sorry, downwards. Now, when it comes to these forces, we got to be just kind of making note of how do they point in relation to the actual acceleration. So we have centripetal acceleration AC, centripetal acceleration AC, centripetal acceleration AC. We've got for our upright cars, a normal force going up, but for the one in the middle, that's going away from the center, a normal force going up, so going into the middle for the one on the right, and then a normal force going down because we are upside down on the first one. These are all near the Earth, so we have a weight going down as well. So we have a W going down, a W going down. We have a W going down. So just take note of the differences here. Here we have all three in one direction. Here we have one going up, two going down, and then we have two going up, one going down. So that's important distinction here. So all three of these are parallel to each other, so they can all have the same sign when we're plugging forces and accelerations into Newton's second law. When it comes to situation B, we want the weight and the acceleration to have the same sign and the normal force to have the opposite sign. You're welcome to stick with up is positive and down is negative for those if you would like. Doesn't matter. As long as we just attribute the signs correctly. And then for these two, these are both going up, so they have to have the same sign, and W just has to have the opposite sign. So again, you could do positive, positive, negative if you would like. There's no reason why you can't. We just have to stick to the convention for how we define what the signs actually are. Okay, so that's what we see here. So with A, you can make them all negative, or you can make them all positive, as I've shown right here for all of these. But again, we've got the same kind of distinction for all those signs. So that's carried through in Newton's second law. All right, so for our first scenario, just make them all positive. They're all in the same direction. That's going to be fine. So we've got normal force and weight working together equals n times v squared over r, which is our acceleration. All three are positive. Okay, weight becomes mg, and then plug in what we know. We know the mass, we know g, we know the speed for the first situation. We know the size of our circle, the radius 100. So if we're getting a value on a scale on normal force in this case, it will be 189.6 when we're upside down at the top of that vertical circle. For context, a 60 kilogram object at rest on the surface of the Earth would give us a weight of 588 newtons. So a much smaller value on the scale is displayed for that first scenario, going upside down at the top of a loop-to-loop. Now for B, we got normal force going up. We got our weight and acceleration going down. So we got to make sure that normal force has a different sign compared to weights and the acceleration. But again, same substitutions basically. W equals mg. And then we're making all of our numbers go, and then we plug everything in, and we get a number. So we get an even smaller value on the scale at the top of that circle, that hill, when we're upright in our car. And then at the bottom of the valley there, again, we've got our normal force going up, acceleration going up, same sign for those two. Weight is the opposite way, so the opposite sign. So normal force, weight, and acceleration all have their signs attributed to them correctly now. W is equal to mg. Again, substitutions, plug them in, let them go. And we get a much bigger number on the scale there, bigger than our actual weight, almost double, actually. So there you go. Now that's important. So big distinction here. If our car is just at rest or moving horizontally on a flat ground, then the normal force going up and the weight going down are balancing each other out. If our car is on a platform that is accelerating vertically upwards and it's being lifted, let's say to have work done onto it, during the period of the acceleration when it's going from not moving to moving upwards, the reading on that scale is going to spike. So our normal force is going to be bigger than our actual weight because the acceleration in the y direction points vertically upwards in that scenario. We have the exact same thing here. It's just not a vertical acceleration that's causing vertical motion. It's just a vertical acceleration vector, which is defining the fact that we're moving in a circle. So not only at the bottom does our normal force just support our weight, but it also does the work to get us to continue moving in a circle. So our normal force when we're at the bottom is equal to the weight plus the actual fact that we're moving in a circle with a centripetal acceleration, and the normal force causes that centripetal acceleration to occur. So the value on the scale, the number of the normal force, the magnitude is going to be bigger than our actual weight. And that's true. It doesn't even have to be a normal force. That could be true for any of our like common forces where we're like moving at the bottom of a vertical circle. So like tension with an object swinging through, like if we have a pendulum, the tension going upwards at the lowest point for that pendulum is not only equal to the weight, but it's equal to the fact that the tension is supporting the weight of the pendulum and getting it to accelerate through the bottom of a vertical circle. So not only does it just hold the weight, but it provides an additional acceleration. So the value of that force of tension needs to be just greater than just the value of the weight. So I think useful and important concept for us to try and wrap our heads around. So there you go. All right. That's our video. Just always double check Schoology to see if there's any other useful things like a checklist or solutions or whatever, other notes, equation lists, things like that, to make sure that you're fully prepared for what we need to do. So if you have any questions, please do not hesitate to reach out. I wish you all the best of luck. Take care.